Is in the literature. Got it. I don't know if it's so much a skills workshop. I'm not going to be doing anything hands-on, but I'm just hoping to give you kind of an overview of like the major concepts and papers in the difference in difference literature that have been developed in the last 5-6 years. And feel free to interrupt me at any point if you have any clarifications. I think the slides I put together are pretty minimal. I'm assuming that those of you who are here are familiar with the like basic difference in difference model. I'll go very briefly over that, but it's kind of assumed throughout. So yeah, if you have any questions, interrupt me, please. Okay, so as an introduction, difference in difference is a simple, intuitive, and powerful method for causal inference with usually observational panel data. It's especially used in policy evaluation. Diff and diff and its extensions, which are regression, diff and diff, also known as the two-way fixed effects estimator. And then regression-based event studies are very popular methods in applied microeconomics. There was a review paper a few years ago. I don't know the numbers, but it's some huge fraction of applied micro papers in the top journals like use difference in difference or some variant of it, like 25% or something. And that's, I would say, since the 90s, 2000s, it's been really popular. Since about 2017, a new literature has been building that points out some serious flaws with the standard two-way fixed effects methods in many cases that they've been applied in the literature. And since these sort of problems have emerged, a lot of solutions have also been proposed. And I'll talk a little bit about some of those. So I just want to walk through the basic issues, like what are the problems with two-way fixed effects estimation as it's usually done, and some of the proposed solutions. So this is like the very basic difference in difference model. So you have two periods of time, like a pre-period and a post-period, and they're the same units observed both periods of time. You have two groups, a treatment group and a control group. Those are usually used in like randomized control trials, but the treatment is the group that has some kind of policy applied to it. The control group is another group that doesn't have the policy. And the thing we're interested in estimating here is what was the effect of this policy in the treatment group? So that's the ATT, or the average treatment effect on the trio. And so this is like usually the diagram you see for basic difference. The key assumption for this model is parallel trends. So in this case, we have a control group here, this orange line, observed at time 0 and time 1. And this y-axis is some outcome. Let's say it's like a schooling program. So like Paul Gillespie has had this study with eyeglasses. So this is like test scores, and the treatment is like the kids get eyeglasses provided. So this control group is people in the school that didn't get eyeglasses. And this dotted line is the counterfactual of people in the school who did get the eyeglasses if they hadn't gotten the eyeglasses. So the assumption here is that the change in the treated schools on test scores would increase by the same amount as it did in the controls. And then in reality, we observe this treatment if they did get eyeglasses. And so we see like this different trend. And if the parallel trend assumption is true, we can look at the difference between the treatment and the counterfactual, which we infer from the control unit. That's the basic idea behind difference and difference. And it's like you can run it in a regression, this very simple equation. You just have your outcome with the intercept plus a dummy for being in the treatment group in the post group. And then the coefficient on this dummy variable, the beta, is your estimated treatment effects.
Hey, Matt.
Yeah.
Melissa online asked if you could raise your voice a bit, project a bit for the, or at least be closer to the mic for the Zoom people.
Yes, I will try. Here, I'll point this towards me as well. Okay, so that's like the basic graph. I always found it was a little bit confusing because I don't know, you can't really see the trend so much. So I just like this. I mean, my drawing is terrible, but I think it's more intuitive to think of this as like in a larger number of time periods, and the logic still applies. So like, suppose that these A, B, and C units are your control units. They all have this similar trend that goes like this. And then there's a treatment of this time T star. Let me move this over here. And then here, D, this is the treated group. D at T star gets some treatment, and its outcomes shift up by this to the red line. But the counterfactual is assumed to be this dashed line, still parallel with all the other units. And so then this difference, which is the same as this difference, is the ATP. What's a really important assumption of this model, which I'll talk about a little bit later, is that these basically this difference here is constant. So if you measure it here right at the treatment time, it's going to be the same difference as measuring it later. Okay. So an extension of the difference in difference is regression difference in difference, or the two-way fixed effects model. So you can extend it to multiple time periods, which is that diagram that I just showed you. You can also extend it to the case where different units get the treatment at different times. And essentially, they just get a dummy variable for being in the post-treatment period, depending on wherever they started treatment. And you can also add covariates to this model. I'm just gonna ignore the complication of covariates. Most of the new models can also incorporate covariates, but I'm not going to cover it today, just in the interest of time. And it complicates things quite a bit, and it has its own set of issues that you need to consider beyond what you would normally consider just in a normal regression model. So the basic two-way fixed effects equation for a difference in difference model, you regress the outcome on this, which is a unit fixed effect, alpha I, time fixed effect, alpha T, and then a treatment dummy, And then assuming everything works out right with the assumptions, this beta is again your average treatment effect on the treated. Okay, so the major complication of this model arises when you have heterogeneous treatment effects. So each unit has a different effect. So unit I has a different effect than unit J for this treatment. So that's like the first complication. The second complication is when those treatment effects vary over time as well within an individual. So I'll talk about both of those cases. Okay. So the first thing I'm going to talk about is when you have this difference in difference, multiple periods, and you have a variation in treatment. So this is one of the first papers, which I'll talk about shortly, is by Andrew Goodman-Bacon. So if you've heard about like your Goodman-Bacon paper, this is like what it's all about. And he just considers the example of standard difference in difference using this equation here, but where treatment timing is different for different units. So the assumptions needed for two-way fixed effects to work in this case, which are derived in that paper as well as other papers, there's two possible cases. So when there's actually no variation in treatment timing, then two-way fixed effects can give you an unbiased estimate for the average treatment effect on the treated. That's even with multiple time periods. As long as everyone is treated at the same time, then it's not really a problem. But when there is variation in treatment timing, you need another assumption. So in that case, if the treatment effects don't change over time, which is what I was showing in this earlier model, where you have the same difference right at the treatment time versus later on. So if that treatment effect is stable over time, then two-way fixed effects is also an unbiased estimator, but it's for a slightly different estimate. Rather than being the average treatment effect on the treated, it's a variance weighted average of the treatment. So you don't average it just like summing up all the treatment effects and dividing by the number of units. Instead, you get a weighted average weighted by the variance of the treatment variable, which is a binary variable. And that weight is highest when that binary variable has the highest variance, which is closer to the middle of the sample. Because binary variables with variance is highest when their probability equals 0.5 and gets lower as you get closer to 0 or 1. So that's, in that case, you still get something like pretty good and interpretable, but it's not quite the EPP. And so this is kind of like the big conclusion of this paper. And I'll just explain a little bit the intuition behind this. So Goodman-Bacon has this difference in difference decomposition theorem where he decomposes the two-way fixed effect estimator into a weighted sum of 2x2 difference in distance estimators, which just compare they choose 2 units out of the total population, split them into pre and post, and then calculate the difference, the simple difference in difference using those. And then the two-way fixed effects estimator takes a weighted combination of all possible combinations like that. And they all have positive weights. if the treatment effects are constant over time. Okay, and then one key issue, which is explained in detail in this paper, is that units that are treated earlier in the sample, their post-treatment period is used as a control for units that are treated later. And I'll give an illustration of this next. So, oh yeah.
One clarification question for people who haven't been in this lab as much. When you say that the weights are positive, are you talking about applying explicit weights, or are you saying that implicitly when you take the average of these multiple periods that it ends up being weighted by the variance?
Yeah, implicit. So this is not using like regression weights. Okay, so here's a diagram, what I just tried to explain. So you have a unit here. This is its outcome measurement over time, and then eventually gets treated and its outcome shoots up. So very effective treatment. And then this is another unit, and it's treated earlier and gets that bump, and then it's measured over time. So what I was trying to explain with earlier treated units, post-treatment periods, used as controls, is in this decomposition, essentially this period, even though it's like after the unit was treated, it's taken by the regression and treated as if it were a control for this one, because this is constant treatment status for this, whereas the other one has a change in treatment status during that period. So these post-treatment observations of the controls. And so in this case, it's actually not a problem, but we still have this difference, which is constant here, and then we observe the change, and that still gives us like an accurate estimate of the treatment effect. And that's because for this, the treatment effect doesn't vary over time. It's the same treatment effect. Where we have problems is when the treatment effects are not constant. So basically, the simplest case is rather than having a level shift like this, the trend changes. So now you have this trend, and then the treatment makes the trend secondary. Okay. Now, when you use this treated unit as a control, you don't. Here's your pre-period, and it's like this average of these various effects. So this pre-period is not an accurate representation of the actual difference in that period. It's being biased because what you're actually observing is a treatment effect that's evolving over time. And so that biases the estimate in the standard two-way fixed effects model. And the next thing I'm going to talk about is event study, which is sort of like a generalization of difference and difference to try to accommodate these dynamic treatment effects. But that has its own complications as well. Sorry.
You get it though?
I think we're good.
Okay.
Is the red light still on by the red button?
Yes.
Cool.
Okay. So I talked a little bit about that decomposition in the Goodman-Bacon paper. Other authors have also decomposed the two-way fixed effects estimand in different ways and found different insights. And so I'm just going to list them here. So for also, if you want to get a complete picture, I recommend checking all of them out. But there's this paper by Imai and Kim, who just published in 2018 or something. Borosiuk et al. 2023. D. Chase Martin and De Fuyu, or however you say that, 2020. And then Gardner et al. In 2023. And I just want to say, I am planning to put together like a list of resources and papers that I'll send out after the thing. I haven't put it together yet. I'm also going to be giving this presentation again on Friday, so I'm going to make sure to have those resources ready by then. Share it with everyone. Okay. So as I briefly mentioned before, another extension of difference in difference is the event study. And this is like difference in difference, except rather than just having a constant treatment effect assumed, you have a treatment effect that evolves over time. So this is like a classic event study plot. Here in the event study plot, you have 0 as like the treatment time, and then like negative numbers are pre-treatment periods, positive numbers are post-treatment, and then you plot the estimated treatment effect in each period. And what you want in these kind of studies is the pre-treatment coefficients to be close to 0. That's often taken as evidence of no pre-trend, which is taken as evidence of the parallel trends assumption. But there are issues of that, which I'll talk about. Yeah.
There are not error bars around -1. Is that because these outcomes have been normalized to 1 unit before the treatment?
Yes, that's correct. And with the event study, rather than just having a level shift in your outcome, you have this treatment effect that varies over time. This isn't the greatest example, but maybe it'll go up like this, or go up and flatten out or something. And the event study models are built to incorporate this kind of dynamic treatment effect. These are also very common in the literature. Yeah. In this place? Here? There's like a whole literature on things, but the basic idea is if these are close to 0 and there's not an obvious trend, then what that means is that before the treatment happened, the treatment and control groups were very similar and moving in parallel, which you usually see as fairly convincing evidence of the trend would also be parallel after the treatment occurred between the counterfactual and control group. This one, yeah, exactly. So what you're really interested in is like these coefficients, but this is useful for assessing how realistic that parallel truth assumption is, because that's a crucial assumption for difference in difference. Any other questions on the basic event study setup? All right. Okay, so the main paper, the first one to really study event studies in detail, was this Sun and Abraham paper, which was published in 2020. Their kind of main result is that the dynamic treatment effects that you saw plotted on that previous graph, when they're estimated by a standard two-way fixed effects model, the estimates in one period are contaminated by estimates from other periods. So what you see here is supposed to be the treatment of the time period 2, but it's actually some, like, what you're actually estimating is some weighted combination of the period 2 effect, period 1 effect, period 0 effect. So that's a problem. And they do decomposition of the two-way fixed effects coefficients and give very detailed breakdown of exactly what's going into coefficients under different assumptions. And essentially, if you want to avoid this, if you want to estimate a event study model, what you need is 3 assumptions to hold. First, you need the parallel trend assumption. Second, you need the no anticipation assumption, which is actually common to all the different models. That means that there's no effect of the treatment before the actual treatment began. So, like me and Thomas studied the minimum wage, there's often concern that wages or employment will start to be affected by a minimum wage before it's even implemented because people are like anticipating it and reacting early. So for difference in difference to work, you need to assume that that's not happening. It's usually fairly easy to avoid by just like changing where you determine the date of treatment is to a time period before you think any anticipation effects are going to occur, but you do need that assumption. So the key finding from this Sun and Abraham paper is this third one, which is that you need homogeneous treatment effect dynamics across all the units. So let's see. I don't have a good diagram of this, but I'm sorry to those on Zoom, but I'm just going to draw something on the board. So,
are you able to turn on?
Can you all see this? Sorry.
Are you able to turn on your camera at all for Zoom?
Oh, maybe I can do that. Let's see. Start video.
You have the background blurred, so turn that off so that people will be able to see forward. There you go.
Okay. Hopefully you guys can see my diagram here. So here's our event study plot. It's treatment occurs at time 0. You have all these observations which are exactly 0 before. And then you have like one unit as this treatment effect over time. Gets quickly improves and then kind of levels off to the same level over time. And then you have another one that's like a sudden jump and then just keeps going up forever. So you have like very different treatment responses to these two units. Okay? So if you try to estimate this kind of thing with the two-way fixed effects model, it doesn't work at all. But if all of the treated units have like, treatment effects of the same slope or parallel like this, they're just level shifts, then two-way fixed effects can recover the accurate coefficients. They still have the issue of like the variance weighting that I talked about earlier with the Andrew Goodman-Bacon paper, but at least you get a weighted average of treatment effects. Okay, I'm going to turn off my video. Okay, so Son and Abraham find this issue, but they actually propose a solution to it too, which is really nice. So essentially what they do is they, rather than just having like, and I apologize for not putting the event study regression equation, I need to add that in. But basically, rather than just having the event study with a single coefficient for each relative time period in the event, like one coefficient for this, one for this, one for this, they add a bunch of parameters, and so every unit that's treated at a specific time period is going to be grouped into a cohort, and each cohort gets its own set of event study coefficients that are estimated. And when you do that, that gives you a proper estimate of treatment effects, a weighted estimate. Again, that has the issue of variance weighting, but they also propose a second step where they re-weight the coefficients so that it does actually recover the average treatment voltage. So like there's software that will implement this. You just like kind of put it in, put your information in, and it does the regression rather than just doing the problematic two-way fixed effects regression. It will do these adjustments to give you identified estimates. And again, I said I would share resources. There's like a lot of different software that will do all of this too. So I'll be sharing resources on like the software packages that you can use for that. Okay. And I really apologize. Like I wanted to talk more about this Callaway and Sant'Anna paper. It's very important, but I just ran out. So I'm going to just cover it very briefly. Callaway and Sant'Anna is like kind of, in my opinion, like the core paper in all this new literature. Once you understand this paper, all of the other papers can be sort of understood in terms of the Callaway's. And what it does is essentially, rather than viewing this difference in difference or event study type model in terms of regression, it does it in a totally non-parametric way. So again, I'm going to write on the board. Okay, so Callaway and Sant'Anna model is based on identifying essentially two types of units. Units that are treated at some point and control units that stay untreated the whole. So what you do is for each treated cohort, so G is the cohort, there will be a set of units that's treated at the same time, a set of states that all increase their minimum, which is the same, for example. So essentially, for each cohort, you do a whole separate estimation. What you do is you like okay, so the Callaway and Sant'Anna model, you have like a base period. You estimate your control outcome in that base period. And then you estimate your treatment outcome in that base period. And then under the assumption of parallel trends, in period one, under the assumption of parallel trends, the treatment would be like that, but maybe it's actually up here. Here's the counterfactual. Here's the actual one. So essentially what we do with Callaway and Sant'Anna is estimate tons of parameters. For each cohort, we take the 1 period difference in difference, which is this. And this is called the ATT GT. This is ATT-G1. So you get the average treatment effect for a particular group G at time 1. Okay. And then this one is ATT-G2. That's just doing another simple difference in difference, but only looking at the 2 periods out. And you can do ATT-G3, ATT-G4, and then you do that for all the different cohorts. G equals all the different cohorts based on treatment. Okay. So essentially, it's just like a difference in units. Really simple estimation, just non-geometric. You can just like program it by hand with a few lines.
And does it make the counterfactual follow the never treated that closely, or does it smoothen it?
So in this method, it does follow it exactly.
Not like that.
And this paper goes into a lot about covariate adjustment to like get a conditional parallel trends assumption. Where it kind of loosens that a little bit, but yeah, it is. Okay. It does assume this exact parallel.
One advantage of it though is that it lets you pick if you want to use a never treated group or a late treated or early treated group as your counterfactual. So if you do the difference between your late treated and your early treated, maybe that's a more apt comparison, and you can be accused of shopping for that, but that can also be a benefit. So
right. No, so my thing is like if I don't know, when you look at a graph like the C over there, right? Like there's like a trend and then there's just some random variation from the trend. And so it seems to me like it would just introduce too much additional noise just because of every little deviation of that curve. Like I would try to estimate like a smooth trend for the never treated, right? And then just take it off of that. That's essentially what the classic Dix and Dix does. Yeah.
And that's what Sun and Abrams do, is it tries to then create these weights to then
Okay.
do that. Whereas Callaway Sant'Anna goes, we're not going to weight this. We're going to let you pick and go through all the whole bones of all of it and see how it works.
Okay.
There are like multiple other estimators that all are based on the same idea, but basically create the counterfactual in different ways. So there are other ones that loosen that based on like estimating fixed effects using only the control units or using covariates and some, and you have to weigh the advantages and disadvantages of each. But there's like 10 different methods.
But the base case just does exactly this.
This is the idea, yeah. Sure. Okay, so once you get all these like hundreds of ATT, GT parameters, you can aggregate them in different ways. So like you could look at, for all cohorts, what is the average ATT G1? And then that's your average effect estimate for one. Do the same for period 2, and that gives you an event study. Or you can just average all of them in the post period, and that gives you like the classic difference in difference study. We're assuming it's just like one fixed treatment. And they go through multiple other ways of aggregating. And they have software that lets you do it pretty easily as well. So it's just like this very simple method that decomposes things down to like the very simplest unit and then lets you build up whatever estimate you want. So that's Callaway's. Any other questions on that? If you want to get into this literature, I would recommend reading the Callaway and Sant'Anna paper. And skip all the stuff about standard errors until you understand all of it really well, because that's like a whole other layer of complexity that you don't even want to get into. Okay. All right. So here's my list of other solutions to this problem, which all more or less rest on very similar assumptions and essentially are just different ways of constructing this counterfactual, as I said. And when I send out this slide, I'll put the years to all these papers too. But there's the Callaway and Sant'Anna, which also has like different ways of adjusting parallel trends for covariates. The Sant'Anna and Zhao paper, the Callaway and Sant'Anna uses the method from Sant'Anna and Zhao, which uses the method from Abadi, Goodman et al. And then Sun and Abraham, I talked a little bit about their method. Borusiuk et al. Uses an imputation method where they construct this counterfactual by estimating unit and time fixed effects just using the controls in the pre-treatment period and then imputing this counterfactual that way, which gives you a little bit less noisy of a comparison group. Chase Martini Oil has another method that they use. Gardner et al. Has this method called two-stage difference in difference, which I'm using for right now. That's actually like the simplest, very easy one. Essentially, you regress the outcome on unit and time fixed effects for all the control units and all the pre-treatment treated units. Residualize the outcome to remove those fixed effects, and then just run a normal regression of that outcome on treatment, and that gets you also the correct estimates. So that's like not much more complicated than just running a two-way fixed effects regression, but it solves all the problems. So I would, if you want to like, if you're interested in doing this kind of stuff, I would recommend first read Callaway and Sant'Anna for background, and then read that Gardner paper. There's another one by Wooldridge called the two-way one-block regression. There's another one called stack difference and difference. There's another one that I can even put on there called local projections difference and difference. They're all slightly different ways of constructing counterfactuals. Yeah.
So I think one of the things for us who are a bit earlier in our stages, I get that we invest in understanding all the different ones, but then how do you select what is the methodology that you're going to use? Because I've seen a couple presentations where people will say, here's 6 or 7 different ways to do difference and difference. My results hold for all of them. And then I've seen other ones where they say, oh, this is the paper we're going to stick with. This fits my assumptions. And that seems a bit opaque to me. Like, how do you go about selecting?
I don't have a good answer. There's like at least 2 review papers, which I'll add to this afterward, that have done comparisons of the different methods. A lot of the differences are just what you think are realistic assumptions for parallel trends, like how you introduce covariates into the parallel trends, whether you want to use only pre-treatment covariates or post-treatment covariates, and there's other considerations in those decisions, which there's like a whole literature. And I wish it was this or a simple explanation, but it's not. The main thing is just like, if it looks like parallel trends are holding, and you have a long period, like the model you use probably doesn't make that big of a difference. And there's this paper by Baker et al. That compares all the methods. In like simulation studies, they all look like almost exactly. They all have unbiased estimates. The standard error, a lot of the difference is in how they estimate standard errors. So when standard errors are a big issue and they're large, like you can see big differences in these. And then really you just like, unfortunately, you just gotta like understand the assumptions that they're using to create those standard errors and how reasonable those are in your context. A lot of it's like how the data was, what kind of assumptions about like a random sample and the cluster sample or whatever makes sense in the data. And some of them do like graphics. Yeah.
So I wanted to ask something about the Woodridge paper.
Yeah.
So I saw a lot of discussion on this at some point in Twitter. And I'm not sure I really understood. So do you have like more context of what it is, like the two-way modular regression?
That's something that I don't understand very well, but I think I feel like it's kind of like trying to collapse a lot of the pre-treatment variation and covariates into like one pre-treatment average and somehow introducing that into a regression. But I very well. I haven't really seen that used too much. I think it's probably because it's hard to understand. The stack difference and difference is also like intuitively simple. Essentially, rather than having like this big data set with different treatment units being treated at different periods of time, you just take the whole set of controls with one of the treatment units and do your difference and difference estimate, and then do exactly the same thing with each other unit separately, and then average the results, and that also gives you the correct answer. So, I mean, if you do all of them and like all of them give you the correct answer, like they should, because they all are based on the same assumptions. But yeah, I think I went to this difference and difference workshop with Janet Johnson and Goodman-Bacon earlier this year. And their kind of big recommendation is like, don't just like run all the models in Syllabus, and you want to like really justify why you're using this model based on your research design. Just like stick with it. It's still good to like run other ones for robustness, but the design argument should like speak for themselves. And then, I think a lot of, at least in my experience with the project I'm working on, a lot of the consideration is like statistical power. Like the Callaway and Sant'Anna, because it estimates so many coefficients, has like really low power. And some of the other methods use a little bit stronger assumptions, which, if they're realistic, give you more power from your standard. So that's like a definite consideration.
Yeah, I actually wanted to have that because I think that when I read this stuff, I noticed that Callaway and Sant'Anna were like the basic one, like they are assuming less assumptions. They also, although they have a couple that are kind of strong about like not turning off treatment or homogeneous treatment effects and stuff like that. Like depending on that, you would choose like Fortitude or Abadi or the other stuff. At the end, what I understood was that it is actually like the safe way is Callaway and Sant'Anna. Like if that one fits, or you get something with that, probably you're gonna get something also with your other models.
Yeah, I think that's fair. Another thing I want to mention that just thought of as you were saying that is all this literature is about like difference in difference two-way fixed effects. Like it doesn't mean that the two-way fixed effects model time and unit fixed effects is necessarily bad in all cases. If you have a treatment that's like varying up and down over time and like not highly correlated, you can use two-way fixed effects fine. And it doesn't have issues. And there's papers showing basically if treatment timing is randomly assigned, then these issues go away too. The issue is when there are like correlations between like treatment effects, treatment timing, essentially. Okay, so yeah, you have another question, Tom?
Yeah, you made a comment earlier that might help to clarify. Positive weighting versus negative weighting. Why do the authors care about that as an issue?
The negative weighting thing, I think that Borsiak paper or Sikadal paper explains it well with a nice little table. The issue with negative weights is that you can get an estimate that's outside the convex hull of the actual estimates. So like all the treatment effects are between 5 and 10. With a negative weight, you can get a treatment effect of like 15, which is really bad. So that's why like negative weights are really bad. And those happen when for units that are treated like really early in the sample or like really late in the sample. Okay, so these are just like other topics that I didn't really cover at all, but they're also like a full literature about each of these in this context. Thanks, Alvin. So like incorporating covariates, like how to properly test for parallel trends, diagnostics that basically you can use to evaluate how good the various assumptions to do two-way fixed effects hold. And if it seems like the issues that cause problems with two-way fixed effects aren't present in your data, then you can just use it and it's okay. So there's various diagnostics for that. There's a whole thing about continuous treatment that's like in its infancy, and then inference and standard errors. So that's all for another day, but thank you all. Any more questions?
Does anyone online have any questions they'd like to ask Matt?
There's one chat. Okay, there are 8 people on the